Good afternoon, everyone. So, welcome to the week 11 for deep learning. So, the previous week, again, we'll be revising the concepts which was covered during this week, and I will be solving some of the problem statement from the last year's assignment problems so that it will be helpful for you to solve your assignments and any of your doubt you are having. So if you have any doubts or any clarification you want, feel free to ask your doubt. Okay. And yeah, so let's get started. Okay. So maybe this week was mainly covered around the sequence to sequence modeling. Okay. So first of all, so I will just give you a small introduction that what's the sequence to sequence modeling is all about. So you can think it of as, for example, the Hindi to English translation or English to Hindi translation. Okay, so you say something in one language, you want to get it translated in another language. So that's kind of a problem statement we are trying to address, that sequence to sequence. Okay, and this kind of a data means why we need this kind of a thing. Okay, so first of all, let me write that what are we covering. Okay, sequence learning. Okay. Then we'll be talking about recurrent neural network. So as of now, we have seen two kind of architectures. First is the straightforward neural network. The second is the convolution neural network. So this is kind of a third neural network which we are going to be seeing. Okay. And we'll be talking about some of the problem statement it's having. That is back propagation through time, vanishing, the exploding gradient. Then we'll be talking about LSTM, long, short term memory. So basically, it just tries to address the problems we are having, we face in the RNNs. So that's the main purpose of having to introduce LSTM. Okay. Then we'll be talking about what the LSTM is made up of, means writing, reading, forgetting, and all. Okay. And finally, we will just seeing that how it means tries to avoid the problem of vanishing and exploding gradient. Okay. And lastly, we'll be solving the problem of the okay week. You know. So again, so first of all, I hope that you have went through the lecture material. So if not, it's better to just go through the lecture material. Okay. So I will be just giving you a glimpse of what was covered during this week so that it will be making our job easier to solving the problems we are having. Okay. So yeah. Okay. So first of all, as I mentioned, we have seen two kind of architectures as of now. The feed-forward neural network, feed-forward neural network, and the convolutional neural network. Okay. Now again, we are going to see one of the new kind of architecture, which is the current one. And the purpose of each kind of architecture is something different. It depends upon the data types we are trying to address. Okay. Convolution is used basically wherever we are trying to do the image processing. where we want to have a filter, we want to define our bases, features, edges, and all. Okay. So it's mainly used for the images thing. Okay. Mainly, it can be used anywhere else as well, but it's much more successful in the image domain, basically, computer vision. Okay. And the feed forward neural network, actually, if you see, if you ask me the feed forward neural network, all the kind of architecture we will be studying, okay, the convolution, recurrent, and transformer. Actually, everything is a kind, it's a special case of a feed forward neural network. Okay. So feed forward neural network is that we have a hidden layers and all the previous layers neurons are connected to the next layer neurons. Okay. So that's the normal feed forward neural network we have seen. Okay. And about this convolution, we have a kind of a spatial arrangement. We know that we have a filters, we just slide it over the image and try to get a feature. Okay. So the main purpose of introducing different kind of architecture, which are subset of this straightforward neural network, is to address particular kind of a bias we want to have in our model. Bias in the sense, for example, as I mentioned, bias is kind of you want to introduce either in your laws or in your architecture so that it's good for modeling certain kind of architecture. So this recurrent neural network, okay. So why we need a recurrent neural network first of all, okay. So suppose the one common problem statement I take, okay. So you all may be familiar with the sequences. Sequences series. We have been there. We have seen this kind of a concepts in the high school mathematics. Okay. So series we define a sequence. Suppose I define 1, 2, 4, 8, 16. So it's just 2 to the power something. It's a sequence. Okay. So for example, what kind of problem we are trying to address is that suppose if I give you 1 and the next sequence is 2, so it should predict 2. If I'm giving 2, it should predict 4. If I give my model 4, it should predict 8. The next. So it's kind of like this. I want to construct a function which take input xn, that's the current index, and try to give me the next sequence member. Okay. So this kind of thing we want to model basically. Okay. And this f is parameterized by the parameters theta, and this theta are the runnable weights for the feed-forward neural network. So in the end, whenever this neural network is coming into the picture, it's just a function approximator, nothing more than it. The main purpose of neural network is to identify the underlying function which is responsible for kind of function we want to model. Okay. So you can try to model y equal to sin x. You just give a bunch of sin y equal to sin x, just sample some sin x points, get the corresponding y, make your data set, train a model, and ask it that if this is my x value, what's the y value? So basically, you are trying to do the regression there. You are trying to fit a sine wave using a neural network. That's the main purpose. Okay. So the sequence. So what's the real life example of the sequences? Okay. So the one common very example is auto completion we are having. So you might be searching something on your Google or something, or you message your friends. So you type that how are you something, okay? And in the previous week we talked about that how to convert this words into the embeddings. So whatever model we are having, we want to deal with the numbers because computer in the end they just work with zeros and ones. Using zeros and ones, we just make integers, float, and all whatever kind of a data type we define. And we feed in particular number, it gives us the particular output as a number. And we have a certain interpretation of that number as an input, means as a kind of a word. Okay. So any algorithm, whatever we are working with, it's common that it should be in the mathematics, means some number format, it should be present. Okay. Okay. So as I mentioned, the one very common example for this is auto completion. Okay. So you give that how as an input, it should predict the next word as a R. If you give R as an input, the model, this is our model F theta. This is our model F theta. U. If you give U as an input, it should predict question mark. And after that, it should just not predict next thing. Okay. So each input is, you can think it of as a vector. In the Euclidean space, each word corresponds to a one vector, and we are trying to learn the mapping from vector to a vector. Okay, so you can think of this as learning a function which take a vector as an input, try to give a vector as an output. Okay, so in simple word, we want to construct a function f theta which take r to the power d, where d is the dimension of the vector, which correspond to the embedding size we are having, and try to construct it as the next output. Okay, and we have we be having on the top of this the loss we will be defining. Okay, and we will be just trying to estimate this loss, minimize using the optimizers. Okay, and so as I mentioned, our machine learning model is just function approximator f theta, which takes input, try to give you the output. We define a loss, the signal, which tells that how good our model is performing. Then we want to update the weight. Optimizer we define, Adam, SGD, gradient descent, RMS plot. It can be anything, literally, okay? And we back propagate the gradient throughout the weight space of our model, try to update the weights. And like this, we try to just minimize as much as possible the loss. Okay, so that's the common theme across the deep learning. You have a data, you define a certain kind of architecture, you define the loss, you define the optimizer, just back to it. Okay, so this is a complete pipeline of any ML model. Okay, so as I mentioned, we are basically thinking about sequence to sequence model, but why we need a different architecture? That's the question which is getting arised. Okay, so the basic thing is the kind of an architecture we have seen. It always take a fixed input size. In the conversation, you train a model, it will be always 32 cross 32, 64 cross 64, 128 cross 128, something like this. The pixel size it sees remains a constant. Okay, because our model which we are making, or so we just make it specific to the particular input size only. Okay, but the thing is, whenever we are coming with the sequences, there is a issue. What's the issue is that? Okay, so as I mentioned, we want to have an architecture which can do sequence to sequence. And how are you? In this case, we were having a three input. How are you basically? Okay. And we know one thing, that the next word is dependent upon the previous word. It's not like that two words are completely IIDs, identically and independent distributed. Okay. It was not the case in feed-forward neural network we were using, or we were using the convolution neural network, where we didn't assume anything. But here, by default, the next, for example, as of now, the current temperature of his room is suppose 44. The next 1 hour, it won't be 90 or 100. It can't change because it depends what the current temperature is. Okay. So it will be 45, 46, 50, something. But it depends upon what was the previous temperature. It does not arises very drastically. There is a relationship between the next time prediction between the previous time. Okay. So basically, we are talking about the sequences. Okay, we are given a sequence. Just trying to construct a sequences. Okay, and the kind of a task is just sequence to sequence, which is very much common in auto completion. You can see, or language to language translation. Okay, question answering, whatever it can be. And this you can think it of as a regression task, taking a previous input, try to predict the next output. Okay. And also we are having one more task, which is classification. We can just on the based on review movie reviews, we'll be asking that how was the movie, whether it was good or bad or something like that. Okay. So, but we need to have a prior information of all the input. And the catch here is that our reviews, the input length, it can be vary between 4 or 5. Someone wrote the movie is very bad. Okay. So there is just a 4 words in this. Okay. And someone just wrote a very detailed description. The movie was very long, boring, and I didn't enjoy it. The hero was something like he wrote it. Okay. And we'll be asking that to classify it as a positive or negative. So the question, the main thing is not a classification is a issue, but the thing is the sequence end as we are working in the discretized world. Okay. So as we are working in the discretized world, so the input which we can give, uh, so you can just give me 1 minute. Okay. So the thing is, the question we are asking is that we have been given a bunch of different movies, very long context thing. We want to classify it, but as the model can't take it can't take it just always take a fixed amount of size. So the one brute force solution we can do is that make all the reviews of fixed length. So if someone is giving 4 and someone is giving 16, make everything the maximum length extended padding. Okay, you can just pad everything 0. But it's kind of a useless. You are wasting a long, means lot of time, memory in that. Okay, by doing computation and all. So the question we are trying to answer is that can we do better? The always the research, I mean, the question we try to address is the brute force coming up with the brute force solution is okay. That's the first step, but we always ask the question related to 2 things: that what's the problem we are trying to solve, and how much computational efficient it is. Okay, multiplying a 2 matrices, it might seems easy to you. Okay, but as the matrix size increases, the order of computation increases to the means O to the power d cube, the dimension of the matrix we are having, and that is very much cubism actually. Okay, means you might not feel that this is just a problem, but whenever you are working with the bigger and bigger metrics, okay, it isn't a problem. It's a fundamental problem, which means today in the literature it is there. Okay, so that's the thing about the sequence to sequence. We are giving input as a sequence. The output is also a sequence. So, for example, the video you can see, you might be seeing some Hollywood movies and all. Okay. So, for example, Iron Man is flying something like this. Okay. So the next the video data set it just composed of various frames. Okay. In 1 second, you see a 16 image frame actually, and that is how you interpret that this is a movie which is getting moved. But actually, it's just an image sequence of images, and the next in frame depend upon the previous one. So if he is flying, then the next time he will be flying a little bit upward. Okay. So that's the thing about this kind of a data sets. Okay. And currently the CNN it always worked with the fixed input size. We want to have a model. Okay. So that is the problem we are trying to solve. Okay. So the thing is, uh, we have been given a sequence x1, x2, x3. Okay, we want to get to a next sequence that is y1, y2, y3. Okay, and we know that the next input sequence depend upon the previous one. and the same holds for the output as well. That's the relationship we already know. That's very much common in time series data, video data, or in the way I am speaking. My name is okay. The next word will is dependent upon what I'm saying currently. Okay. So this kind of a data sets, there is a lot of problem and data set we can have all this. Okay. So the thing is, we take first we want to construct a model which take x1 try to predict a y1 as an output. Okay. Take x1 and x2 and try to predict the y2. Take x1, x2, x3 try to predict y3. But the things you see, this all is represented as a function. Okay. So the issue here is that a function is dependent upon the number of words we are trying to see it, the embedding dimension. It increases as the number of this thing. So it's not possible actually. Okay. We always want to deal with one model. We don't want to have a lot of models for the different length size. No, that's we don't want. Because for example, human brain is there. Okay, you can speak right. Okay, suppose if I give you a new task, you won't be like that. My brain can't do this. So brain can do it. That's the thing. We want to have a one common model which can take any amount of input information what is getting fed and try to complete the task which we want. Okay. So that's the thing we are trying to ask. Okay. So now you might have been knowing that we wants to construct a function which can take a variable in size length of input as an input, variable size inputs, okay, and try to predict the output. But and that's the one thing. The second thing we also know is that in the input there is a relationship that is the x1, x2 is dependent upon x1, x3 is dependent upon in turn dependent upon x2, which implies that x3 depend upon x1 as well as on x2. Okay, so we want to have model something like this, and the current architectures are unable to model such kind of a data. Okay, so one very much common thing we can do is that we are having an x1 as an input, u as something, it can be a neural network or anything. Okay, and it will be giving you s1 as a input output v, it will be giving you y1. Similarly, we'll be having x2 u, it will be giving you s2. What this s2 and all are, I will be just stating you know. So basically like this, we are given a sequence. U, V are my model parameter. Either you can take it as a neural network or you can take it as a matrix. Okay, anything it can be. S1, S2 are the hidden representation. So the thing is, what we are trying to do is that this hidden representation, the next initially we are having x1 as an input to our model, and it's giving us some hidden representation. Hidden representation in between there something, some information. Okay, and after that we are just passing to the model v. Okay, and it just try to give us the output. Okay, but also we can try to do for the as many x2. Okay, but the thing is, this kind of a model, we can again take any length and we can pass it again and again. Okay, so that's kind of an issue we don't have here. We can take copies of model, same models, again copy, we can pass my, it will be giving next word, name, something, okay. But it misses one thing, because as x2 is there, x2 depends upon x1, and also y2 depends upon x1, x2, okay. So this two x1 and x2 are not completely right. There is some correlation is there, okay. Correlation in this means some hidden thing is there which is connecting both of them. What I'm gonna speak next 5 minutes. It depends upon what I have spoken in the last past 5 minutes, something like this. Okay, but how to decide that what I want to speak in the next 5 minutes? It's already depend upon the past previous minute. I was trying to say the context I'm trying to convey, the meaning. Okay, so the hidden representation, we'll be having one more block of W, which take the previous input representation, multiply it, we'll be adding it here, okay, to the S2 and passing with the model V, and which will be giving us the corresponding output. So now the thing is that this hidden representation, which in turn depend upon the X1, so our Y2 now will be a function of F and X1, comma X1, comma X2, X1. Like this, we can take again and again for the n amount of sequences. Okay. And the beauty for this kind of an architecture, which was very brute force thing actually. The brute force in the sense we wanted to pass an in fundamentally long sequences. Okay. And it should give us the output. But the thing is, there is only a certain kind of fixed size input we can only pass to the model. Okay. So basically this SI, the hidden representation, you can think it of as X U of Xi plus B. This B is bars you just you can take as a matrix, represent as a neural network, and sigma is the non-linearity activation we are having. Okay. So this is the normal sequence to sequence modeling you can think it of. And yi you can think it as O. O is the output we want to do classification or whatever. Yes. C. Okay. So I is the time step. Also, this thing is there. We are this is the normal thing without the connection, but here we be adding W S I minus 1 as well, because we want to model take the previous input hidden representation also into our model. Okay. So actually, this kind of a model is very much common in the controls and all. And it's control theory in the electrical engineering. Okay. So the thing about this model is that we want to model a sequence basically. And for sequence to sequence, we want to that the next time step, whatever we are predicting, it should be depending on the previous time step, whatever we have already had. Okay. And I is the time step. So how does this kind of an architecture matter? For example, the chat GPT you might have seen, but in the backbone, it uses a transformer. That's a different thing. You just give it as input as certain paragraph asking what's the correct, can you teach me this something? Okay. So what it wants to generate, that's the input sequence. It needs to it needs to do give the output, which is another sequence. That is the answer. Okay. So what it does is that it will be generating one word at a time, and it will be feeding that auto-regressive and try to predict the next word. So that's the hidden mechanism of ChatGPT. The next word it may predict depends upon the previous contexts, whatever it is already predicted. Okay. Because that's how you can reason. For example, if I ask you to write a step-by-step solution, the next step depends upon the previous step. If you don't, if your previous step is wrong, the next step is already wrong. So that's the thing about sequence, means this kind of an architecture why we need. So I hope you got glimpse that what exactly we want to do. Okay. So compactly, you want to represent this kind of an architecture. You can think it of as we are having a hidden representation, outer representation yi. This is our matrix V. This is our matrix Xi. And this is our matrix U. This is V. And here again, looping with the W matrix. So this is the looping mechanism which is already happening. Okay. Now, if we are being familiar with this concept of what I say, uh, matrix theory, basically, okay, then you might be seeing again and again we are multiplying W. Okay. So for example, the X1 is there, means Y1, sorry. So in this week lecture, they talked about the back propagation through the time. Okay. So let me write you what's actually the back propagation through time is. Okay. So initially, the Y1 is there. The S1 is sigma time U of X1 plus W times S0 plus bias. S0 by default you can take it as a means starting vector which is composed of zeros. And Y1 is just O of V of S1 plus B. Okay. Now this is just a recursion which is happening actually. Okay. Now what is a recursion? For example, you want to calculate the sum of any series. What you do? The summation over I from 1 to n. So if I want to add 1 plus 2 plus 4 certain for 100 terms, and suppose I don't know the formula of how to sum up this geometric series. So what I will be doing? I will be just having one variable output. I'll be looping over each element, try to sum it and add it my output. So that's a recursion. Again and again, I'll be looping through the input sequence until what number of sequences I want to sum it up. And I will be getting an output. Okay. So suppose I expand it. Okay. Now S2 is there. It's just sigma of U of X1 U of X2 plus W of S1 plus B. Okay. So what was my S1? My S1 was here defined. So this S2, you can think it of as sigma times U of X2 plus sigma time U of X1 plus W of S0 plus B plus again B, which is coming from here. Okay. Now you can see this is a chaining which is happening. If we write S3, then this will be the S2 which will be coming into the picture and you can expand it. You can see there is some pattern which is getting observed. Okay. Now the thing is, this is the S1, this is the W. Yeah. Now initially here was what W. Here if you see, if you remove this non-entirety, suppose for simplicity, okay. This is W times U, this is W square. Then it will be becoming with the time as my sequence and get bigger and bigger 100. So it will be W to the power 100. So now the question comes, what's so there is a standard result in the matrix theory, and you can write W, you can do the eigenvalue decomposition, okay, or you can do SVD, okay, and write represent W as U to the U sigma V. Now, if you do W to the power n many times, you can write it as U sigma to the power n times V. Now, if my this is my diagonal matrix, we know, and if my diagonal element are one, there is no issue. With the time, it will remain the one. But if my diagonal element are different in the sense less than one, then as n increases, this sigma n will tends to zero. If my elements are more than one, then it will explode. That's the vanishing and the exploding gradient. Okay. So this was in a different manner what was covered in the week lectures. So I wanted to give a different notation because this sigma, you can ignore it. You can bond it actually. Okay. So I guess in the week lecture, it was shown using the bondedness. Okay. So, and but the thing is now if you want to update the weights, okay, the output is wrong at suppose after 110 by sequence to sequence I'm doing auto completion. The third word is wrong. The word is wrong because the second word was wrong. Second word was wrong because the first word is what it's predicted is wrong. So the value we will be back propagating again and again with the in the time the sequence from where this error came into the picture. And that's much more visible from this equation as well we are having. Okay. So that's the only the back propagation through time we are having. Okay. And doing this back propagation, as I mentioned, you'll be getting this. It depends upon the eigenvalues of this W transpose W thing. Okay. And this sigma controls your vanishing and exploding really. Now, the question is, what else can we do? Means, can we control the behavior of a system as my sequence? And because we want to have a longer reasoning. If I'm speaking, it should not be I will be I'm just speaking something meaningful in the 5 minutes, and in the rest of 45 minutes it just blah blah something. Okay. So it should be able to reason for a longer amount of time. If it's not, it's doing kind of a hallucination. So that's the common term which is getting used everywhere in LLMs. Okay. So what the hallucination is there? You ask the chat GPT a very big question. After some time, it will be giving you some rubbish answers. Okay. So because it's working for the shorter range, it can't reason for the longer range at all. Okay. So this was the introduction about the RNNs. So the output function, if we want to do the classification of a movie rating positive means it was whether good movie, bad movie. You can do a softmax, normal classification upon reading all the input hidden representation and repeating this looping thing. And the loss for the classification, it's always cross entropy. Loss for the regression, normal mean square error you can do. Okay. So now the question is this auto completion. The auto completion, you can see it as kind of a regression term. I mean, so more than regression, it's more kind of a, what I say, classification. You can see it as why it's a classification problem is because we, for example, I'm writing my name is I'm doing this thing auto completion word letter by letter, suppose not word by word. I'm doing letter by letter. Okay, if I type my, I know there are only 26 alphabets. So the total number of classes are 26. Okay. The next word it needs to predict should have a more probability for Y. Okay. So you can generate a distribution. Basically, my name is something, my MY, then space bar, name, NAME. Okay. So it's kind of more kind of a classification task. Okay. So the content which this week cover is kind of a little bit outdated content, but it's good enough to know that it was existed in a deep ending in the last decade actually. Okay. So why it became uses it will become clear in the next week, the transformer, because it just took it over this thing. Okay. So vanishing gradient and exploding gradient problem we discussed. Okay. Now let's coming back to this LSTMs. Okay. So the main issue we were facing is basically due to this eigenvalues for this sigma thing. This UA and V are the different orthogonal matrix. Okay, don't confuse with the UA and V I have used in the model description above. Okay, so the thing is, we in the prediction for the next time, we are trying to use the prediction hidden representation for the prediction as the previous time step and try to merge it. It's kind of some linear. This is kind of a linear thing I'm doing. I'm trying to add a previous time step to the current time step input and try to predict the output at the current time step. Okay. So as I mentioned, if I am very long context, so if my output is long at 100, suppose time step, then again it needs to back propagate the loss till the first time step, and that's kind of a very tedious task. Okay, because you need to back propagate again and again. The more number of looping you are using, the more number of time backward you need to go back. Actually. So there is more kind of a thing, okay, more new concepts which was built on the top of RNN to counter its. It was performing initially good, but the training as the sequence ends get bigger and bigger. It's a tedious task because today, for example, the transformers, chat GPT, you are just passing a 1,000 words and again going 1,000 backward. The training, it's computationally not efficient. Main deep learning architecture is going in a two ways. The first one is related to the mathematical concepts which is getting developed. Okay. But the second thing is experimental computational thing and all. So a lot of research is just to make the model faster in inference, computationally efficient, okay, lesser data, more generalization. Okay. So one common thing is that whenever you're solving a problem, okay, we always solve a problem sequentially. Sequentially in the sense, suppose if I ask you, prove that sum of angles of a triangle is 180 degrees, suppose, okay. So first of all, you'll be just making a triangle, having showing the vertices A, B, C, D, making an angle alpha 1, alpha 2, alpha 3. Okay, then you'll be making another line parallel to that and showing this alternate angles are equal and all properties. And then again, finally, you'll be conclusion as the using the lemma which you already know. The angle made by a straight line is 180 degree. Okay, so that's kind of a you be proceeding with. Okay, so we always write something, and if because and the previous time step basically we want to forget it actually. Okay, so if I'm at the current time step, I will current step of proving. I just need a previous step what I proved. I don't need a very top step what I proved actually, because that's the sequential proof we do. And based on this analogy, for example, you solve a problem on board. You write, teachers write some problem, a solution. They just some of the thing which is not needed. Okay, and that's the kind of a forgetting you can think. Okay, and again they build up on that. So that is based on read, write, and forget. You read content which we already know. You write based on that, and forget whatever you have learned already. Okay. So based on this concept, a new kind of an architecture was proposed. Okay, new kind of a mechanism. Okay, that how our brain stores the information. So you might have seen, for example, that 20, for example, if you are currently 20 into 20 more than 20 is okay. 20 year back, what happened? You won't be remembering properly what happened exactly whenever you were a child. Okay, you just remember properly the last 1 year, 2 years. Okay, as the time progresses, your memory become means you can't able to recollect everything actually. And that's what the common reasoning is all about. We just try to give more emphasis to the latest information and try to forget the unnecessary thing which happened in the past. Okay. So based on this analogy, another kind of an architecture is developed. Okay, where this hidden representation we had. Okay. So there is a very good example which was covered in this week, that compute is ABCD value has been given. We want to compute AC, BD plus A plus AD thing. So this is just a sequential step which happens in the calculator anything. So we want to just at each and every step, we want to decide what to write, what to forget, what to means this thing. Okay. So it was mainly based upon the hidden representation we had, because this hidden representation becomes w to the power ns. So this w to the power n, it is an issue which makes its eigenvalue means so this singular value either tends to zero or explode. That's the only thing. If we can able to control it, that's good actually. Okay. So the intuition basically about this was on the read, write, and forget. Okay. So we have a information intermediate representation SI, where I denotes the time step I am. Okay. Or either HTIV following. Okay. So I want to selectively read, selectively write, and selectively forget the data. Okay. So it's like this. This is my input at current time step. This is my previous time x t minus 1. I want to compose this and give an output for the next representation st. Okay, which will be good used in the next consecutive steps. Okay, and initially what we were doing is we were using u and w. We'll be getting non-linearity after summing it up and all in the normal RN. And we saw that there was an exploding gradient and vanishing gradient issue. So what was proposed is that have a gating mechanism multiplied with the another vector of the same dimension. Okay. Suppose this is O t to the power minus 1. Okay. Means O t minus 1. Okay. So what does it say is that it will be just doing a fractional thing that this information is better. It's kind of a, I am having a gate which controls that how much information should pass to the gate, because not all the information is needed. So, for example, if you are writing an exam, you might have mug up the whole book, but in the exam, whenever you see the questions, you might be forgetting the unnecessary thing which you were remembering again and again that this was some certain concepts. So that's the thing only. We don't want all the information which was needed to predict in the next time step. So this is we are doing with the gating mechanism. Okay. So it will be giving us a certain representation of ht minus 1. Okay. And again, we are gonna run this ot minus 1 and all. Okay. And it gave us the representation ht bar. Okay. I'm not covering in depth the equation wise. You can just go through the material for this week. Okay. So this ht bar again we defined this was the lighting mechanism. Again, in the reading, again, reading gate was proposed. Okay. So it was I to the power it, which we control at how much information we want to read the representation we had. Then again, we'll be having forget gate. Okay, how much information do we want to forget actually? Okay. So ht minus 1. Okay. How much previous time information we want to forget it. And again, maybe having another gate. Okay. Which is just forget gate ft. So we have used the initial gate. We read how much information we want. We multiplied it with the gating mechanism, got it, st bar. And we want to read how much information we want to read. And the previous time step, how much information we want to add and propagate through this gate. Okay. So that was the only thing actually. There isn't any lot of means what I say theoretical guarantee for this that why it should work. But the thing is, it makes sure that whenever you are doing the back propagation, the vanished the gradient does not vanish. It does not tend to zero. So because having this kind of architecture, it makes sure that we are having a multiple paths and the gradient can flow through the multiple paths, so it won't be a zero in at all. Okay. And for the exploding gradient, nothing can be done. Okay. So the only thing was just clipping the gradient. If my gradient is getting bigger, just make it lesser. Okay. So that was the thing which was covered. So let's come back to solving some of the problems. Okay. So we have been given and following RNN, and we are also given the architecture for this RNN. Doesn't include W connecting the states of the network. Okay. So it's going like this. The first question. This is H naught, the hidden representation. This is X1, which is giving output Y1. And again, it's giving H1 as the hidden representation. And again, the X2 is going to the input and Y2. It's giving us the output. So like this, we are having the thing, and this network architecture, it looks like it's having a two input. It's a feed-forward network in the end, but having a control. Okay. So this is the architecture we are having. Okay. So two inputs. So you can think it of as two input, two output thing. Okay. How many neurons are in the hidden representation at state S2? Instead of S2, it's H2 they are asking. How many hidden layers at state S2? So see, the only thing is there is a looping mechanism which happens. Okay. So the number of neurons hidden here is three only. Okay, the solution for this thing is three because the architecture is fixed. It does not depend upon the state which where we are. Okay. The number of neurons will remain the three. So the first answer is three. The second answer, we have trained the above RNN and it has done the weights and bias accordingly. If the weight of H1, X1 to H1 at S5 is 2, what will be the value of same weight at X6? If the weight of X1 to H1. Okay. So they are saying we are having this representation to the well. This weight is W, certain what weights is there. Suppose it's 2. Okay. What is the same weight whenever we are reaching either 6 times 10? Weight remains the same. The answer is the neural network, it does not depend on whatever time step you are. The weights, the architecture, everything is fixed. Okay. So the weights remain the same for the RNN at all the time. The third question. What's the dimension of the matrix W which connect states in RNN? Okay. What's the dimension of W which connect states in RNN? Okay. So since the number of neurons we are having actually here, the hidden representation is 3. So the weight matrix W will be R to the power D plus D. So D is the hidden neurons I am having, where D is equal to 3. So the answer is R to the power 3 plus 3. So that was the first three question. Okay. Now the fourth question. We have been given an RNN with the norm of the W matrix is 3.5. This is a norm of the W. Just take a matrix and make it a vector out of it. The rows concatenate those along same dimension, and then take a normal norm of vector, whatever you are having, L2 norm. Okay. The activation function used in the RNN is logistic. Okay. So 1 divided by 1 plus e to the power minus x. That's the activation function which is used. What can we say about the activation is logistic? What can we say about the gradient, which is dou of S? Dou of S 20 divided by dou of S1. So this 1 sigma of x is just 1 plus e to the power minus x. Okay, that's the logistic regression we are having. And if you take a derivative of this logistic regression for this, it is upper bounded by 1 by 4. So that's the exercise why it's 1 by 4. You can take a derivative of 1 divided by 1 plus e to the power minus x. Okay. Okay, take a derivative and it will be always less than or equal to 1 by 4. It's always less than 1 by 4. Okay. So the gradient it is gamma. Okay. The gamma is less than 1. Okay. Due to backpropagation to the state in the SI. Okay. So basically this is S20. From 20 we are taking with the hidden representation S1. Okay. So it's gamma to the power n minus 1 where it will be 19. Gamma to the power 9. Okay. It's 1 by 4. So it will be 1 by 4 to the power 19, which is means very much close to 0. Okay, so the value for this is approximately equal to 0. So it's a hidden representation derivative at time 20 with respect to hidden representation at time s1. And we saw this, there is a recurrence relation. You can expand it and you can see the pattern actually. Okay. The fifth question. What are the problems in the RNN? Morphing of information stored at each time step. Yes. Exploding and vanishing gradient problem. Yes. Error caused at time step Tn cannot be related to the previous time steps far away. Yes. Okay. Error caused at the time step Tn can't be related to previous time steps far away because there is a vanishing thing. So the answer is all of above. Now the sixth question. Arrange the following sequence in order they are performed in LSTM at time t. Selectively read, selectively write, selectively forget. So first of all, we do the reading. Okay. Then we forget the data and then we write. So the correct answer is read, forget, and write. RWF. Okay. How does LSTM avoid the problem of vanishing gradient? Okay, we use a different activation function. No, activation function remain the same. Forget gets control the flow of gradient in back propagation. Yes, forget get it controls the flow of gradient. We normalize the gradient during back propagation. No, landing rate increased. No, it's due to forget gate. Which type of neural network is best suited for sequential data? It's RNN. Okay. What is the objective function in RNN? Okay. So basically we are doing the sequence to sequence. Okay. Cross entropy, sum of cross entropy, squared error, accuracy. So it's just a sum of cross entropy loss we are having actually. Okay. So because why it's a sum of cross entropy? Because we are having a time step. So it's summation of one time 1 to t, the cross entropy loss at particular time step. Okay. So it's sum of cross entropy. Then select the task for which the RNN will work better than other types of networks. Video captioning, language translation, image detection, sentiment classification. Video captioning, because the next time step is dependent on the previous time step. So whenever we are doing the video captioning, it's true. So the first one is true. Language translation, it's a sequence to sequence from English to Hindi. We are going one word is corresponding to the another word. Okay, so that's also true. Image detection, no, it's just a fixed input. We want to detect the image. Okay, and lastly, the sentiment analysis. The sentiment analysis is the review of the movie. So we want to read the previous the reviews and then we want to classify it as good or bad or whatever. Okay. So the correct answer is ABD. Okay. So that's all for the today's lecture, guys. So I hope you enjoyed the session. So let's meet next week again, okay, for the final lecture.